Hello everyone, welcome back to the another session in Design and Analysis of Algorithms. The topic name is Satisfiability Problem. This topic you'll find in 5th unit as topic number 3. Now let's get started. Prior to this topic, there are two topics what we were made two videos. There we've come to know two things that are, the first thing is about deterministic algorithms, non-deterministic algorithms. Deterministic algorithms which takes polynomial time and each and every step we know it. Non-deterministic algorithm will take exponential time. Correct? And from the second video, we understood something that deterministic algorithms are taking polynomial time and we'll find out the non-deterministic algorithm which takes polynomial time, not exponential time. Because the calculating of exponential time is waste because you don't know whether what are the steps which you don't know are going to be part of the non-deterministic algorithms. Hence you will be calculating the non-deterministic algorithms which takes polynomial time. So these are what two outcomes what you know from the last videos, correct? Now the very interesting fact is what exponential time taking algorithms are. What algorithms we have? 0 by 1 knapsack problem, traveling salesperson problem, Hamiltonian cycle, graph coloring, all these problems. The point is what? If we were unable to solve, at least to show the relationship between them, such that if one problem is solved, it should be easy for solving other problems also in polynomial time. We will not work on each and every problem individually. So how to relate them together? That is the big question. That is the next thing we will learn. So for relating them together, we need some problem. That the problem is what? Satisfiability problem. Now what do you mean by satisfiability problem? We will be going to solve this problem. If one problem among this is comes under satisfiability, then all the problems will comes under satisfiability. That's what the relating the problems. If I'll solve this satisfiability problem and I find this satisfiability problem from this exponential time and one of the problem is related to this problem, hence both problems are satisfiability problems. That means we will be finding the relationship. Let's talk about what is satisfiability problem. So satisfiability problem is what? Consider a CNF formula, that is propositional calculus formula. This is what? Propositional calculus formula. It is dealing about the set of some Boolean variables x1, x2 till xn or xi denote Boolean variables. When I say it is Boolean variables, the result of these variables are true or false. Now, let xi is denote with the negation of xi. A literal is either a variable or it's a negation. That's what you could able to see. These are what literals and you can find the literal or it's a negation. Now, a formula in the propositional calculus is an expression that can be constructed using literals and the operations and are. And or. Example, and this is what, if we do have two classes here. This class I am pointing out with a C1, this class is C2. So it is having two classes, let's say it is C1 and C2, are formed using disjunction and they are joined with the conjunction. So this is what CNF formula is. A formula is in conjunctive normal form. The satisfiability problem is to determine whether a formula is true for some assignment of truth values to the variables. CNF satisfiability is the satisfiability problem for CNF formulas. This is what the definition. Satisfiability problem is what we'll find out for what values xi this formula is true. Now let's take Now what is satisfiability problem? Satisfiability problem is to find out for what values xi or this CNF formula is true. So what are the possible values of xi? I have three, let's suppose that I have taken three variables, literals, and these three variables values are what? So these are what? Boolean values, so it can be of 0 or 1. That means I have three variables x1, x2, x3, and those are what? 0, 0, 0, 1, 0, 1, 0. Like this I'll get what? How many? 2 cube possibilities. That means there are 8 possibilities. I should try all these 8 possibilities. Now this is what 2 power n means exponential time. This problem solution is expected in exponential time. And this is what? If satisfiability problem is exponential time, that means whatsoever algorithms I have from the first slide which produces exponential time, knapsack problem, traveling salesperson problem, Hamiltonian cycle, graph coloring, all are exponential time. Now satisfiability problem is also exponential. So I am just adding satisfiability problem here. Now the point is, if I could able to solve the complexity of satisfiability problem, if I could able to solve satisfiability problem is belongs to deterministic algorithm with the polynomial time, hence all other algorithms are also polynomial time. If I could able to solve this satisfiability, saying that it is a P problem or it is P subset of NP or it is P is equal to NP, then all other problems are the same. Because if one is belongs to one set, the all other belongs to this same set. And that is what we are going to find out, the relationship in between satisfiability and this. Right? Now, so let's solve this satisfiability problem. How to solve this satisfiability problem? So I'm just taking three values. For that I'm generating the state space tree. So state space tree I'm generating that x1 is equal to 1. So x1 value can be 1 or 0. So after I take x1 value, now I'm just taking x2 value. It can be also 1, x2 is 0. Now x1 is 1, x1 is 0. And now add even x3. x3 is equal to 1 and 1 0 1 0 1 0 1 0. The solution of this state space tree is what? From leaf to root or from root to leaf. That is, what are the possibilities of satisfiability problem 2 power n? That is 1 1 1. It is one of the solution. 1 1 1 1 0, one of the solution. 1 0 1, one of the solution. 1 0 0. So like this you can find 2 power n, that is 2 cube is equal to 8 possibility solutions. Now let's say that I have erased satisfiability problem. I have erased all these things and I have shown you only this diagram. So this diagram is looking like what? A state space tree to solve knapsack problem. Correct? If I take out all these things, if I say that only this diagram is presented and if I ask you to recollect for what this diagram is, then we can make sure that to tell this diagram is belongs to knapsack problem. Because now let's see, if I draw a knapsack problem also it will be the same. Now I'm taking some example, knapsack problem example only. So that is what? 0 by 1 knapsack problem. Profits are some 10, 8, 20, whereas n is equal to 3. Weights are 5, 4, 3, where m is equal to 8. Now how we'll solve this problem? The reason, the expected solution of this problem is what? I can include the object in the knapsack or not. I cannot include or include. I cannot include or include. The solution is also expected in Boolean, true or false. Now, state space tree, if I construct that also the same as like of your satisfiability problem, correct? So now satisfiability problem is also same as 0 by 1 knapsack problem. That means both are related. The time complexity of satisfied problem is 2 power n. One of the non-deterministic algorithm, which is 0 by 1 knapsack problem, complexity is also 2 power n. Now I am adding this satisfiability problem under the list of exponential time. So what did you understand out of it? That we are relating satisfiability problem with exponential time. That means with non-deterministic algorithm. If I could able to solve satisfiability problem, then I could also able to solve all these non-deterministic algorithms with the polynomial time. Now that means, so we will be finding the relationship in between these two. Now let's talk about this, that an algorithm A is polynomial complexity if there exists polynomial P such that computing time of A is equal to big O of P of n, right? Because we could able to solve this satisfiability problem. Now that is, I'm putting satisfiability problem into P. But what the reason? P is the set of all decision problems solvable by deterministic algorithms in polynomial time. There is one more term which is NP. NP is the set of all decision problems solvable by non-deterministic algorithms in polynomial time. Now, since deterministic algorithms are just a special case of non-deterministic, you can watch the last video to understand this, because before merge sort comes into picture, we know about bubble sort, and the time complexity of bubble sort is what? We know big O of n square. Till merge sort till it is discovered by some researcher, binary sort, bubble sort complexity only we know and we feel that it is the best one. When merge sort came into the picture, and it is the best algorithm with the complexity of big O of n log n. So whatever we don't know for time being, that it is of non-deterministic. Whatever you know, that it is of deterministic algorithm. Now the same case, non-deterministic algorithms exponential time we don't know, but one day it will be known. So that's what we could able to calculate non-deterministic with the polynomial time. Now since deterministic algorithms are just a special case of all deterministic algorithms today came from non-deterministic algorithms. All non-deterministic algorithms one day will become deterministic. That was the relationship in between. P is always subset of NP. What we don't know and what has become perhaps the most famous unsolved problem in computer science is whether P is equal to NP or P not equal to NP. This is the most research problem in computer science, not in the computer science. Is it possible that for all the problems in NP, there exist a polynomial time deterministic algorithms that have remained undiscovered? No. To say that, we have a Cook's theorem, that's what satisfiability relation with the reduction. So what is that satisfiability problem is respective to the reduction and to implement the Cook's theorem? Satisfiability problem is reduced to 0 by 1 knapsack problem. Reduction have a transitive property that satisfiability problem is reduced to L1, then L1 is reduced to LT. This is what transitive closure property. Now if satisfiability problem is reduced to 0 by 1 knapsack problem, 0 by 1 knapsack problem can be a parameter to reduce the other non-deterministic algorithm. So this is what actually a transitive closure from the reduction to relate satisfiability problem with the non-deterministic algorithms. Now let's see Cook's theorem, which gives you a famous well-known ideology that it is basically all problems are NP hard problems, and with NP hard you will be finding some satisfiability, that NP hard problem which is having polynomial time. Now let's look at, there is a problem of NP. NP is what? Non-deterministic algorithm which is polynomial time, non-deterministic algorithm which is exponential time. The common point is what? NP complete. That means the problems which are takes polynomial time. Non-deterministic algorithm, polynomial time, that it is what? Satisfiability, that you could able to solve it. Now we already come across with the P and NP relation in the previous videos. Everything is not known to us. Simple, very simple. Nothing is known to us, and for time being we will be going to discover one by one, and that was what P. So everything you don't know and you are coming across with little. So one day it will grow like NP. And what satisfiability Cook's theorem is? P is a subset of NP and P is equal to NP. The reason is what? So satisfiability was having an intersection with this part. P is having an intersection with satisfiability NP and NP hard. So when satisfiability is belongs to P, one day it will get grow and one final day it will be becomes to P is equal to NP. So to prove this one, we do have a Cook's theorem. Now let's see that Cook's theorem. Theorem is what? Satisfiability is in P if and only if P is equal to NP. Now we are now ready to define the NP hard and NP complete classes of problems. First we define the notation of reducibility. Note that reducibility will give you the property of transitive closure. Now let us assume L1 and L2 are problems. That means L1 reduces to L2. L1 reduces to L2 if and only if there is a way to solve L1 by deterministic algorithm with the polynomial time using deterministic polynomial, L2 also polynomial time. Right? Now, this definition implies that if we have a polynomial time algorithm for L2, then we can solve L1 in polynomial time irrespective to the transitive closure. One can readily verify that reduction is a transitive relation, that is L1 reduced L2, L2 reduced L3, L1 reduced L3. So this is what, if I could able to do it now, so that I can solve all your non-deterministic problems with the polynomial time, and one day all non-deterministic algorithm will be deterministic. So this is what Cook's theorem, and this diagram is well-known diagram what you are supposed to keep in mind. So NP, and it is what? NP complete satisfiability condition, and it is what? NP hard. Thank you all.